Good morning, good afternoon, wherever, depending where you are. This is our third keynote lecture, and we are very privileged to have Professor Raquel Urtasun joining us today. Raquel is both a chief scientist and the head of the Uber ATG in Toronto. She's a full professor in the Department of Computer Science at University of Toronto. She's a co-founder of the Vector Institute for AI. Before that, she was an assistant professor at TTI in Chicago. She was visiting professor at ETH Zurich, and she got a PhD degree from BFL in 2006 and went to continue with a postdoc at MIT and Berkeley. Raquel is a world-leading expert in AI for self-driving car, and she has received a slew of awards. I'm not going to read all of the awards, but I will just mention that she's one of the 2018 top influencers as per Adweek magazine. So as we said, we're very privileged, and I'm really looking forward to Raquel's presentation on self-driving car. So Raquel, I pass it to you, and can't wait.
Thanks, Gerard, for your kind introduction. I'm very excited to be here today talking about a future with self-driving cars where they are everywhere. So let me just share my presentation with you. Great. So in this talk, I'm gonna talk about what my team has been working on in the past couple of years as a way to bring self-driving cars to every one of you. So the first thing to think about is that which things are required in order to bring or to accomplish self-driving cars at the scale. On one side, you need the ability to build vehicles at the scale. You also need the ability to operate fleets of cars. You also need to build the brain of the self-driving car such that it generalizes to many places in the world that you haven't seen before, or many situations that you haven't experienced before as well. And lastly, you need a network platform. The car ownership model, as you see it today, will drastically change with self-driving. Instead, you will get your self-driving car as a service, which you will call with the push of a button in your app. This will be a seamless experience where you could combine your self-driving car ride experience with other ways of transportation, such as public transit, bikes, going to the train station, etc. Okay. Today, I'm going to be focusing mainly or mostly in the brain of the self-driving car, which I'm sure that all of you are excited about learning more about. And in particular, I'm going to structure the talk where first I'm going to talk about autonomy, so how to try to go and solve self-driving. And then I will be talking in the last part of the talk about simulation as a way to both test the performance of self-driving cars, as well as test the safety, as well as a way to actually train AI systems for self-driving cars at scale. So let's dig deep into it. So let me tell you how we can use AI in order to create this brain of the self-driving car. A very popular approach that we see a lot in academia is to train a neural network for the task of driving. The input to such a system is a set of sensor measurements, and this can be LiDAR, cameras, radar, and the output is the information necessary for the self-driving car to drive. For example, the steering command and acceleration. The advantage of such an approach is that it is very easy to get a prototype with just a few lines of code in your favorite PyTorch TensorFlow environment. Furthermore, the system is trained for the end task, which is the task of driving. This means that every time that you will make improvements, basically you will be driving better. However, this paradigm has several disadvantages that prevents this from being a true approach to solve self-driving. First, it is difficult to incorporate prior knowledge. And this makes the system, for example, in order to respect the rules of traffic. It also has no interpretability, which poses a problem for the system validation and safety. An alternative, which is basically what you will see everywhere in the industry, is a traditional software stack. The way that this works is the following. Every fraction of a second, the vehicle senses the environment. This is illustrated here in the picture with a bird's eye view of the LiDAR point cloud. So imagine you are on the sky looking down into the self-driving car. The first task that you need to do is to localize the vehicle. Typically, we do this with precision of a few centimeters. And this is done not only to route the vehicle from point A to point B, but also to utilize high-definition maps as prior knowledge for subsequent tasks. The perception system is then responsible for estimating where the objects are in the scene. Here, I'm depicting this with bounding boxes for vehicles and circles for pedestrians. The prediction system, or motion forecasting system, then takes the output of perception and estimates the potential trajectories that the actors might take in the next few seconds. The motion planning model then focuses on a region around the self-driving car and estimates the safest maneuver towards the goal that the vehicle should do in the next few seconds. The control system then ensures that the trajectory we intended to follow is the one that is executed, as there might be deviations due to unaccounted factors such as, for example, friction, or the fact that the vehicle dynamics we might suppose might be a little bit different than what the vehicle actually does. This full process from the sensor measurements all the way to control is repeated every fraction of a second, typically 100 milliseconds, which is the frequency of typical LiDARs. The advantage of this popular paradigm lies in the fact that we have interpretable intermediate representations, and it's easy to incorporate our prior knowledge. However, reaction time is typically large as computation of these models adds up. This also prevents you from having the greatest latest in every one of these models because of this computational budget. Furthermore, developer productivity is very low, as any changes done in one part of the stack will affect the entire stack, and engineers need to manually adjust their algorithms to account for those changes. Now, when you are in industry and you have many hundreds of engineers working on this software stack, this actually becomes a real challenge. Furthermore, the different models are not trained for the end task. So although you might see AI in perception or in prediction, they are trained for surrogate functions that actually do not correlate well with how well you do the task of driving. And as a consequence, even if you improve, say, your perception system, you might end up with worse driving. So what is the vision that I laid out 4 years ago that we've been executing at Uber ATG? So our vision is different than any of the other competitors and has the advantages of both modern AI and traditional engineering approaches, but without inherently the respective drawbacks. In particular, I believe in having a single AI algorithm that can automatically adjust itself to any changes. Thus increases significantly the developer productivity. This doesn't have to be done manually anymore. As computation is now shared across models, the resultant reaction time is also much slower, so you can drive safer. Furthermore, we produce interpretable intermediate representations and allow for the incorporation of prior knowledge to guarantee, for example, that we follow the rules of traffic. And unlike existing approaches, our AI system does complex reasoning, resulting in much better motion plans. Finally, since the approach is trained for the end task, every improvement results in better driving. Our first attempts in order to do this vision focus on having a single algorithm that was able to do perception and motion forecasting. The first version of this, we actually showcased it to the public more than 2 years ago with Fast and Furious, and it was a fairly simplistic approach where the idea is that you're going to have your LiDAR, voxelized LiDAR. You're going to run through a neural network to get some feature representations that represent the scene. And then basically from there, you will provide, you will do detection, and you will regress the potential trajectories of the different actors into the future. So this simplistic approach turns out that it worked extremely well and was much better than the traditional perception and prediction algorithms. Furthermore, the single neural network can run in only a few milliseconds on board the vehicle. So I'm showing you here the results of, this is almost 3 years ago now, of how we could detect, all the different vehicles here. We could also track at the same time, so the same color represents the same vehicle. And the other thing that you can see is these dotted points emanating from every vehicle basically represent the motion forecast for the next second into where everybody's going to be going. If you see a single point, like all those vehicles start parking, means that we expect this particular vehicle to not move in the future. So one thing to notice here is that self-driving is fairly complicated, right? Scenes can have a lot of different actors and doing very complex stuff. Now, if you think about this approach, right? So it's great that we can do this, very fast, but it has a main problem, which is that the prediction of every one of these actors is done independently. And as a first attempt, this is fine. But what happens when you do this is that you can end up with situations like this, where you can have, hopefully you can see this. Cool. So what happens if you predict independently is that you can have solutions for every actor that look reasonable, but as a whole, these solutions might not be reasonable and result in collision. And we know that there is very low probability of this happening. However, if we are able to reason about the interactions between all these different actors, we should be able to predict as a whole a situation that is much more realistic in terms of what we expect to happen in a real situation. Now, the question is, how can we take into account the interactions of so many actors, right? We have hundreds of these actors in the scene in a way that is computationally very efficient. So the way that we achieve this is the following. So first, we're going to enhance the approach to not only use LiDAR point clouds, but also to use high-definition maps. And this is important for motion forecasting because typically what you do in the future really relates to how the particular map. We're going to compute some representation of the scene. And then basically, we're going to do detection and pull important features that are going to be able to give us information about every one of the actors. And then we're going to use a sophisticated, spatially aware graph neural network in order to do the interaction reasoning between all these actors. And this is a way to very efficiently have this reasoning, while at the same time have a fairly sophisticated way of understanding how everybody relates to everybody. And then at the end, we're going to provide a marginal distribution over the trajectories of every one of the actors. But this marginal distribution, as I said, will take into account the interactions. So this is a much better way to actually do prediction. You end up with this nice, probability distribution about the future, and at the same time, you get much more reasonable estimates in terms of, how everybody, like in this case here, reacts to everybody else. So this was a step forward in terms of now thinking about, how the different actors, sort of react to each other. However, if you look at the model that I just presented, and also the literature as a whole, the problem is that at the end of the day, everybody is looking at, can I model the marginal distribution for every actor? And even if you take into account the trajectories of the possibilities of every other actor, at the end of the day, when you go to motion planning, you still have margins, and that is not sufficient. Let me illustrate this with an example here. So imagine we have these two cars where one car is trying to incorporate into the lane of a car that is coming as well. So one possibility is that we predict that the first car is going to yield to the other car. Another possibility that we might, if we sample from the marginals, that we might predict is that this car is yielding and this guy is actually going forward. One more possibility that is, less likely, but we could potentially predict when we sample from the marginals to say that both are actually yielding to each other. So that's already not great, but it's okay. Furthermore, we could actually very likely predict the fact that both are accelerating and they will result in a crash. So despite the fact that we have these interactions, right, we're actually not really modeling how the scene as a whole might actually evolve. So there is a need for really having models that are computationally efficient, but at the same time are able to really take into account the joint distribution of all the actors in the scene. And when you actually sample realizations, you should sample from this joint distribution, not from marginal distributions. Now, the question is, can we actually do this? Computationally, this is very, very complex, right? But can we come up with a way to do this such that we can do this only on a few milliseconds for many samples? So it turns out that the answer is yes. The way that we can actually do this is through what we call an implicit latent variable model, where the idea as before is that we're going to have LiDAR data, we're going to have high-definition maps, we're going to compute some feature representation, and given for the scene, and given those, once we do detection, we will compute some actor features that are deep features from the network. And then basically we're going to have an encoder that is going to create a latent representation for the full scene. This encoder is a graph neural network, again, spatially aware, meaning that the latent variable representation will take into account all the interactions. The other thing that is interesting is that we're going to model this latent representation in a distributed manner, such that no matter how many actors we have in the scene, we can actually capture this very gracefully. And then given this latent representation, which is where all the stochasticity is captured, the decoder is deterministic, and it also uses another graph neural network to, again, take into account all the correlations between this distributed latent representation. Okay, so inference will be very simple. You have your new later representation, your high-definition maps, you do a forward pass, you compute, you pass the messages with your graph neural network, you sample from the latent representation, and you basically decode. So you can do this in parallel extremely fast. The other thing that you can do is that it's actually not too difficult to train this model. And the way that you can do this is basically, you can think of this model as a sophisticated conditional variational autoencoder. I say sophisticated because there is a whole bunch of graph neural networks and other things on it. And in the underlying latent graph representation. But you can train it very similarly as you will do with a CVAE, where you have your KL loss, and at the same time you also have your reconstruction loss that says that given input data from the later and the high definition map, you should be predicting things that are very similar to what you observe in reality. So it turns out that when we compare this model to everything out there in the literature, including, for example, multipath is Waymo's way to do motion forecasting, this implicit latent model works extremely well, as you see here from the metrics, in terms of how consistent the predictions are. So in this case, this metric shows whether your predictions will have collisions, and also in terms of how accurate you represent what actually happened in practice. In this video, you can see the model working, and you see that when it's required, like in this case here, you see multimodal distributions. When it's very clear what the different actors are doing, then you will see that the model captures with a single unimodal distribution. In this case, right, you can turn a continuous trade as an example of how it can very gracefully model these multiple modes of the distribution. The thing that is very interesting is that you don't need to explicitly capture modes per se, as other techniques do with mixture of Gaussians and things like this. Here is much more implicit. Sorry. And you see that all these representations are really consistent scenes for the full scene. Now, it's important that this actually does better than the state of the art, much better than the state of the art in terms of prediction metrics. But what is more important is if we actually hook up this perception prediction system to motion planning, is the result something that works much better in terms of the task of driving? So here we're going to hook up the state of the art, so every possible technique sort of out there, to the same motion planner, as well as our approach. And then we're going to look at metrics in terms of safety, which will be collision, as well as other types of metrics. And you see here that this implicit latent model not only does much better in prediction, but also results in much safer metrics. In this case, these are open loop metrics for safety, as well as you drive more comfortably, and then you typically are closer to what the human did in terms of imitation learning. Okay, so it's safer, more comfortable, and more accurate with respect to what you intend to imitate. So this is sort of like the next generation of joint perception and prediction algorithms, where a single algorithm can do, can detect where everybody is in the scene, can predict what is going to happen into the future, taking into account all these interactions in a way that you do joint reasoning. But if you think about the problem of driving, right? So what happens is that in this case, let's look at a view from the top. some of the actors that you see in the scene, you have a lot of observations, right? You have a lot of, for example, lidar points, a lot of pixels in your cameras, or a lot of radar returns. And then in this case, right, it's fairly easy to do, very accurate perception, and in general, easy to do accurate prediction. Now, in some other cases, for example, if you're far away, you see very little evidence of what is there. And it's actually extremely difficult because you're bounded by the sensor data, right, to understand what's happening. And this is not just about far away. There is many areas that you actually don't see because of occlusion, right? This can be occlusion by, for example, other actors, occlusion by some static part of the environment, right? There's many things that actually will prevent you from seeing. And then, there might be things that are very, very close to the self-driving car, where you actually have no ability to really understand what's happening there. So in that sense, right, this really limits the task of driving, of how well you can actually understand and predict the future. However, if you think about that, if you fast forward into the future, there is not going to be just a single self-driving car in the environment, right? There is going to be several or many self-driving cars driving around. So chances that in the same scene you have several self-driving cars is actually quite high. So what I'm going to talk about next is, can we leverage vehicle-to-vehicle communication in order to see further, in order to see through occlusions, such that we can actually have a much better field of view and we can do much safer self-driving. So I'm going to illustrate this here with a particular set of scenes. In different colors here are vehicles that are self-driving cars. These other vehicles that you see over here are vehicles that are not self-driving cars, or they are not in the range of operation that they can transmit to the different self-driving cars. Okay, so we have a scene that has a mixed fleet, right? You have regular drivers as well as self-driving. And what you observe here is, given the scene, how each self-driving car, and different colors correspond to the different vehicles, how each self-driving car will actually see that scene, right? So there are different viewpoints of what's happening in reality. And the question is, well, now that we have different self-driving cars, which information should we transmit such that we can get the best in terms of improving the safety and the accuracy of our perception and prediction systems, while at the same time not requiring a very large bandwidth for the transmission? So let's see what are the alternatives. One thing that you probably are thinking is, well, we don't want to lose information. Let's just transmit the input data. So I can transmit the radar, cameras, etc. And then basically every self-driving car will receive tons of sensor data from all the different vehicles. Now, the good thing is that the information is preserved. The bad thing is that, well, this is very expensive to transmit. We're going to need a network that is, can actually have, very, very large bandwidth, and that's problematic. And furthermore, the receiving vehicle, now, it was already difficult to process in real time its own sensors. Now it has to process sensors from many different vehicles, right? So this is not going to happen. An alternative is to say, well, instead of doing this, why don't we do perception and prediction for every one of these vehicles, and then let's just independently, and let's just stream the output of these systems, and then we will recorrect our inferences in all these different self-driving vehicles. The good thing about this is it's very compact. Sending bounding boxes and trajectories is only a few bytes. Now, it's very limited in expressiveness because you have already lost information about everything about the environment, about all the scene context, etc. And every time that you make a mistake, this mistake is potentially going to propagate, so resulting in worse safety. So our alternative of what we propose is something different, which is to say the following is, let's treat this as a distributed computing system where you can think of every one of these self-driving cars as a node. And these cars are going to, given their sensory data, they're going to compute some intermediate representation that is learned such that is extremely compressible, so that you don't need a very high bandwidth, but at the same time maintains all the information necessary to be as good as if you actually were to transmit the full sensor data. Okay, and then we will transmit this information, and then every self-driving car will receive this information and leverage this in order to do safer predictions. So let's see how we can leverage this information. So imagine a scene where, let's say that this is the self-driving car that we are being driven in, and there is a whole bunch of other self-driving cars in the scene, each one with its own sensory data. Now everybody is going to do some processing, right, with our network, right, in order to a neural network, in order to produce the intermediate representations, which are obviously different for every one of these cars, since they see also different parts of the scene. Then everybody's going to compress their representations, and it's going to send this representation to the medium, to the channel. Then every car is going to basically receive this information from the other vehicles. And then we're going to use a spatially aware neural network to aggregate the information from all these different sources of information from the different vehicles. And it's spatially aware because we need to understand where everybody is in the scene in order to have these special feature representations to talk to each other. And then finally, we will do some more processing, and we will output our joint perception and prediction. So it turns out that this actually works extremely well. You can do you can do perception much better than this is mean AP, right? Average precision. If we look at if we don't have vehicle-to-vehicle communication, this is absolute points, and this is if we have with our approach vehicle-to-vehicle communication. So you see that it's like a 20-point difference in terms of AP, in terms of how well we can actually do perception. And there is also a big difference in terms of how well we can do motion forecasting, right? So we can see very significantly improve the safety of self-driving cars by using vehicle-to-vehicle communication. Furthermore, you're probably thinking, do we need a lot of vehicles in order to do this? Well, it turns out that the more vehicles or percentage of the SDVs that you have in the scene, the better you do, and it scales basically linearly as a function of how many vehicles you have. And that actually is, it's great to see that it doesn't saturate, right? The more, sensor data and information that you can have, the better that you can do. Now, in terms of with respect to aggregating or sending information about just the LiDAR of the sensor data, or just sending information about the outputs, which are the two baselines that we see over here, which are LiDAR fusion and output fusion. Using this spatially aware graph neural network that also takes into account reasons about delay in transmission, right? Because this is, an asynchronous system that you need to take into account. It turns out that you can do, you can be much better in terms of how well you can handle, for example, the fact that you might have imperfect localization of where every vehicle is with respect to each other. And it's much more robust to maybe you have delay messages due to computation, due to maybe some cues before you send the information, etc., compared to all these other different approaches. So you get much more robust technique by using this V2V-net, right, this spatially aware graph neural network, than if you use more traditional approaches. So this is great, right? Now we are able to think about single algorithm can do perception, prediction, and can actually do vehicle-to-vehicle communication and aggregate stuff across many vehicles, right? All with a single algorithm, right? So that's a big deal in terms of simplifying the software stack. The next I'm going to talk about is, can we actually go all the way to motion planning and control by extending the single algorithm to do basically the full autonomy? And I'm going to talk to you about 3 different generations of technology that we have built in terms of end-to-end interpretable neuromotion planners. The first version of this that we did, we treated as multitask learning, where the idea again is that you have your LiDAR, you have your maps, you do your favorite neural network processing, you can do detection, and you can predict into the future. And on top of this, we're also going to predict a cost volume for motion planning. So what is this cost volume? Basically is spatiotemporal. So these 2 dimensions, this is where the self-driving car is at time t0. This is the area around the self-driving car. And this is the temporal dimension. And what every cell in this cost volume means is what is the cost for the self-driving car to be at every point in time in every spatial location. And how can you use this for motion planning? So it's very simple. Is imagine you have a trajectory that you want to evaluate how good that trajectory is. And this trajectory is, different timestamps where you want to be in the future. So basically, you can cause this trajectory by simply indexing the different points in the volume. So this is something that is an operation that can be done extremely fast on GPUs, right? You have a tensor and you just index on that tensor. And then basically by summing all these different costs, you have the cost of a single trajectory. And this is just some pooling operation in this tensor. Right, so how do we do motion planning? We can sample a whole bunch of trajectories, thousands of these trajectories that are physically realizable. And then basically we cost them all by this very simple processing on GPUs. And then you basically do a mean pooling operation where you select the trajectory that has the minimum cost. All these are just standard operations in your favorite framework. In terms of learning, so you can learn everything end-to-end with a loss for detection and prediction, so you maintain interpretability. And then in the case of planning, you cannot have a direct loss in the planning volume, because otherwise you will already know how to do motion planning. But we can do imitation learning, where we have a max margin loss that basically penalize things that are different than the human. And you also penalize things where the actual trajectories are not safe. So you can have your hand-coded sort of safety requirements there. So how well does this work? So this actually worked pretty nicely. And I'm going to show this in terms of, okay, so these are the detections, the predictions into the future. And for the cost volume, because it's three-dimensional, I'm going to project it to 2 dimensions. Different colors will be different timestamps. And I'm only going to show you the area of low cost. And this is important because basically this is just showing what the vehicle is thinking, which is in red here, of doing. And then in red, trajectory is basically the minimum trajectory cost. So you see here that it could turn or it could continue. It knows things like nudging or changing lanes, because these guys basically are going into you, and it can do very, very complex maneuver like super nudges, like nudges as you see over here. And all this is learned just from data. Well, typically, to create a planner with all these capabilities takes many, many, many months with a team of 100 engineers to do so. So this is a very big step forward in terms of this end-to-end interpretable motion planners. However, there is a few issues that I'm going to talk to you about that will help me motivate the next approach is how to solve this. So the first thing is that, well, if you look at the trajectories, we were looking at, this work was done almost 2 years ago now. We were looking at only predicting a single mode for every trajectory, right, for every vehicle. And we know that this is not necessarily a good idea, because if you get the mode wrong, you might actually decide to do something that can end up, in a bad decision. Furthermore, it was a multitask learning approach, meaning that condition of the features, perception, prediction, and motion planning were independent. And that's not a good idea either. And the other thing is that, yes, we use rules of traffic in terms of the loss function, but we didn't use this in terms of the model itself. And, to me, this is problematic because we cannot guarantee things like we will not collide or follow the loss of traffic or follow some of the dynamic constraints. So the next approach that I'm going to talk about is how we can actually address these 3 issues in a way that is much more sophisticated, but we still maintain this computation efficiency. So we want to use the prior knowledge, we want to explicitly condition on prediction, and we want to have multimodal distributions. So I'm just going to give you a glimpse of this model. Okay, it's fairly complicated, so I'm not going to go in details, but just the gist of what were the design choices that we had. The first thing to note is that it's looking more and more as a traditional stack, right? We have detection, prediction, and planning module. The difference is that instead of having a very compressed state in terms of we will only reason about bounding boxes and their trajectories and maybe their uncertainties, we are going to index back into all the feature computations so that every one of these models can have arbitrarily complex costs. And that's very, very important. The other thing that we have is that, the other thing that we have is that the prediction model now is going to be a sophisticated deep structure model, where you can think of this as an MRF with deep potentials, where every actor in the scene is aware of everybody else's. And then we basically have potentials capturing how good every trajectory is for every one of these vehicles in isolation, and pairwise looking at, will I get into a collision or not? Is this something that will respect, will be infringing, a penalty on everybody else's or not? And then finally, we have a planning model, which is a combination of prior knowledge as well as learned cost functions. And all these things can be actually trained end-to-end by just unrolling message paths in your belief propagation of the prediction model. So the good thing that this thing can capture is the fact that it's multimodal distributions, right, for every one of the actors. The uncertainty, very nicely shown here with colors, increases as a function of time, which is, a desired behavior, right? Because the more that we want to predict into the future, the more uncertain we should be. When things are pretty clear, then the uncertainty, right, is very concentrated. Maybe speed is the only thing. When we are turning lanes, we're turning where we could potentially go into different lanes, we see this multimodality very naturally arising without bothering us in other approaches as I want X modes of the distribution or anything like this. In this case, is implicit, is much easier to handle all these things. So this is showing, in this particular case, open loop scenarios here. Self-driving car and its plan are in red. The predictions that we have multimodal distributions, right, for every other actor that we detect are with different colors over here. You see that we can do fairly complex maneuvers. We get very nicely the uncertainty, and in general, this results in better prediction metrics than the state of the art, and basically almost zero collisions in terms of our predictions into the future. And in terms of planning metrics, also improves very significantly by training all these things together. So this was our second generation, and this is, again, there's quite a big jump in generations, right, where we leverage a lot of the things that we learn about motion, prediction in the models that we develop also for just joint perception and prediction. However, if you think about the task of driving, there is still one thing that actually bothers me quite a lot, which is the following. If you think of these detection-based approaches to driving, what is the problem with them? Is the following. Imagine that this is the situation that we are in. We are in red as a driving car. So what happens here is that if for whatever reason we have little evidence of this car, maybe what happens is that it's going to be below the detection threshold. And as a consequence, if we have a detection-based approach, basically the system will go blind thinking that there is nothing here, despite the fact that there is still some evidence of, there might be an actor or something there, and therefore we should not accelerate and go forward in this intersection, right? So these detection-based approaches are actually not safe. So instead, the third generation of this that we developed, which we call P3 for safe motion planning, so safe perception, prediction, and motion planning, basically what we did is we got rid of detection altogether. And instead, what we're going to do is when we process as always, the LiDAR points, your camera data, as well as your high definition maps, we are going to directly create a semantic occupancy forecasting that is going to be semantically aware. It's going to understand classes like vehicles versus pedestrians. It's going to understand which traffic is opposing to us versus not. But instead of going through detection to create these occupancies that we typically do in self-driving, here we will predict that semantic occupancy directly and use that to create our cost functions for motion planning. And since we don't rely on detection, we remove the need for this thresholding. That basically is the piece that makes self-driving not safe. Okay, so how can we instantiate this? So as I said, you have your radar points, you have your high definition maps, you compute some representation, you fuse it, and basically you have these recurrent updates that are computing these occupancies for the future recurrently in terms of predict time t+1, t+2, t+3, etc. into the future. And then given that, I'm going to create the cost of my motion planner that basically is going to be the following. We're going to sample a set of trajectories. We're going to evaluate those trajectories. And the costs are going to be a combination of, we will, for example, try to avoid areas that the occupancy says that is occupied, right, so that we don't have collision. We're going to try to drive comfortably. We're going to try to drive, follow the route, right, because we're going to go to point A, from point A to point B. And we're going to do things like, we're going to try to drive in the center of the lane so that, you don't do maneuvers that are risky, etc. So you have this combination of learning costs as well as more safety, human hard-coded cost. And then basically, given a set of trajectories, we evaluated these trajectories and we pick the one with the minimum cost. Okay. You can train the whole system end to end, and this is actually important. This is a very, very stable system, which is better than the typical mixture of Gaussians, detection-based stuff that you see in the literature, or you see in some of our competitors. And basically, we have a cost entropy loss for the occupancies, and then we have an imitation-like mass margin loss for in terms of the planner. And this type of planner is actually much better in terms of both open loop and closed loop. Today, I'm just going to show you the open loop metrics. Closed loop metrics is also very, very much more performant. But basically, you get better collision rate, better imitation with respect to the human, and better comfort metrics. So let me show you this with an illustration here. This is again open loop what I'm showing. And so there is a past that we have observed. And then since it's open loop, I'm going to show you the predictions into the future. I show you here what actually happened and in terms of the bounding boxes. But what I'm not showing, so the approach does not take that future evidence into account, because this is again an open loop setting. Okay, and then you see, you get these nice potential multimodal distributions of where things can be. It reasons very nicely implicitly about occlusion. For example, like this occluded stuff here, I can reason about multiple types of actors. And in general, this planner in closed loop is very, very significantly better than anything that you see out there. And closed loop is really what you care about. So I talk a lot today. I started with how can you do joint perception prediction. We went into different levels of complexity of taking into account interactions, multiple vehicles in the scene for vehicle-to-vehicle communication, to how to do end-to-end perception prediction and motion planning, right, with different generations. And in the remainder of the talk, I'm going to talk about a little bit about simulation. So simulation is very important in terms of how to evaluate self-driving cars. But typically in the industry, we use a combination of three things. Structure testing, this will be the test track where you have this repeatable with your dummies test, which is good because it's high fidelity, it's reactive because it's in the real world, but it's not scalable, right? And it's difficult to do safety critical things because you will have crashes. You have a real world replay where you just replay your logs and you see whether you see differences. But this is, it's not reactive, so it doesn't give you super a lot of signal. And then simulation, but the problem with the simulation out there is that, typically it's not high fidelity. So let's talk a little bit about simulation. Now, the perception stack, right, has this perception, prediction, motion planning kind of models. And typically what you see in the industry is that when people use simulation, they start with bounding boxes, right, representing the scene and the actors, and then they test motion plan. And these bounding boxes don't necessarily have the characteristics of the noise of what really happens in practice. It's very complicated, the structural noise that, typically your perception and prediction system has. So as a consequence, you have this overly positive estimate of how well your motion planner is going to do in practice. So you can't really use this to make a safety case. So what's the alternative, right? The alternative is if you're able to have a very precise sensor simulation system that can run in real time, and it's very important that it has to run in real time, then basically you will be able to do this closed loop simulation where you will be able to test the full system end to end. Okay, so let's see how we can do very accurate sensor simulation. All right, so I'm going to start with later, and then I'm going to show you cameras. And if you look at out there where, basically the industry is going, is that they have these virtual worlds, whether it's Carla or, their in-house Unreal simulator. And then basically you have a renderer that uses physics in order to render how the scene looks like. Now, creating all these assets of the vehicles and the scenes and whatnot is time-consuming. It's very expensive. It doesn't scale. It has very little diversity. And typically, if you want to have real time, then it's very, what you obtain at the end is unrealistic simulated data. Instead, our approach is very different, and it's based on the following premise. We have driven millions of miles. So we have observed the world. So what we're going to do is, instead of having artists to generate the world, we're going to use these logs, these millions of miles, in order to recreate the world in terms of the static part of the environment as well as the dynamic objects. And then we will use these assets to recreate new scenarios in the areas that we have driven. So in our ODD, our operation domain, with scenarios that we have, particular scenarios and interactions that we have never observed in the past. Okay, so this is actually outputs of our reconstruction, so we can very, very accurately reconstruct the different scenes. These are real streets, in this case in Pittsburgh. We can reconstruct thousands and thousands, tens of thousands of these assets. And as you can see here, they have very, a lot of diversity in terms of, of the different, these are real world things that we have just observed by driving around. And then we can create scenarios. And these scenarios, we can create them by saying, okay, by hand, we want to test a specific thing. This is what typically system engineering and testing cares about. We can take these logs that we have observed and automatically recreate the scenarios from there, and maybe change the particular actors or where they happen. So the static part of the environment. Or we can use AI to create these scenarios. Okay, so this is what I'm showing here. In this case, we have a probabilistic model that you give it a map, you give it a location of the self-driving car, and basically generates for you very realistic scenarios that could happen in this particular location. And in stochastic, so you can generate many, many variations of these scenarios with all the different actors, taking into account all the dependencies. What else can we do? So we can do, we can go one step further, and then basically not only simulate where they could be and their velocities. Here, what I'm simulating is all the behaviors of the actors for many, many seconds into the future, taking into account all the dependencies. And you can see here, we can simulate some, non-compliant behavior, and we can generate very different STP profiles, all this automatically, and we can do this at scale, right? And basically, this is just a very complex AI system that is able to reason about how everybody potentially will behave as we enroll the simulation. Okay, and what is important and different than the typical thing that people use, like intelligent actor models, etc., is that we can have these very complicated maneuvers, U-turns, non-compliant, as I said, behaviors, as you see here, where we wait for this guy to come, and then we basically perform a maneuver. We can merge and do things like this also. All right, so now we can simulate this. We can create the scenarios automatically. We can create how everybody reacts to everybody automatically. And then the next piece is that we can simulate the sensors, right? And then basically test our perception, prediction, and motion planning. This is what you are observing here, where on the left-hand side, we have the LiDAR simulation. Our LiDAR simulation now is a combination of physics as well as AI. And AI is important for the noise. And on the right-hand side, you see the real LiDAR in a similar scene. And in green, you see the output of the perception system in both simulation as well as LiDAR. And what you can see is that actually it does exactly the same thing in a simulation as well as LiDAR. And this is extremely important. The fidelity is very, very high, meaning that we can test the safety of self-driving car and make the safety case with this technology. Right? So how does this compare to other things? If you run the same type of scenarios in real data, you have this level of performance, for example, for perception metrics. If you run the same scenario kind of in Carla, which is what typically people use, you have a huge performance difference. So you can't really use this for testing. And in our case, you get basically almost the same performance. This is tested with many thousands of logs. Okay. So you have this high level of fidelity, you have confidence that this is a real way to test safety of self-driving. You can also use this to enhance the system and train the perception system. In this case, this is if you only train with simulation, what will be the mean average precision. So take 100K examples from simulation. You can add a small number of real scenarios. Then if you only train on real, you have lower performance. If you add the synthetic, you get better performance. And then you can continue adding more and more real, and you get better and better performance as well. So it's just an enhancer of the real data as well. You can create safety critical situations. In this case, this is the scene that, again, we can create automatically. We added a vehicle here that is basically preventing us from seeing this other vehicle that is going to get into our lane. We created a safety critical situation, and then here you see the closed loop where we can test our self-driving vehicle that basically slow down to take into account this vehicle. Okay, and here you see again our later simulation and the output of perception. And this is not just about one scenario of safety critical. You can generate this at the scale. This is many of these scenarios generated by our later simulation. Now, I show you a lot of vehicles, but we can also do this in the context of humans. Humans are difficult because they're deformable, right? And in this case, and this is the first time I'm showing this. So this is, I guess, a premium for WACB, where the idea is that with a single LiDAR sweep and a single image, which is this data here, we are able to reconstruct the shape of the humans. We are able to reconstruct their skeleton and pose. We are able to also reconstruct skinning data that is necessary for reanimating this human, all fully automatic and at scale. And then as a consequence, right, given these reconstructions, what you can do is you can reanimate this human that you have only one image and one LiDAR sweep from. Right, and this is, and you have very complex shapes, right? We can do things like helmets, backpacks, different clothing, all automatically from just, as I said, a single LiDAR sweep and a single image captured by our self-driving car. You see here the backpacks that we're able to reconstruct. So this is a very, very big deal for self-driving, but this is also actually a big deal if you are, say, Amazon, and you want to clothe people or sell them, clothing features or whatever you want. Here I'm showing that, single LiDAR sweep, as I said, single image, and we are just reanimating automatically this particular human to do all sorts of things, and you see the deformations and everything that we automatically capture from this data. And this is in the wild, right? This is just the self-driving car driving around, right? And we can just reanimate and create our pedestrians to do all sorts of things, and then just simulate them. And of course, very important not to be biased in terms of what human you can reconstruct. So gender, right? So we can reconstruct different genders, different ethnicities, etc. And I'm just showcasing this in this case with a female, right, that was just running around. We only saw this pose, but we can, get this the reconstruction of this female to do all sorts of different things automatically. And the last thing, in the last 2 seconds, I will show you that we can actually do this with cameras as well. So what we're going to do again is using our logs, our raw data that we capture with these millions of miles to reconstruct assets, right? And then we're going to insert these assets in a way that are photorealistic, take into account the 3D, and they take into account traffic as well. Okay, so we can automatically reconstruct, again, just by driving around these assets. And you see here that we have really nice textures for the assets. And then basically, I'm just going to show you how we can reconstruct this. And let me just put this here.
Like the video simulation. For each sequence, we first show the geosim simulation at real-time speed, and then the slowed down version. Notice that our simulated images are temporally coherent, and that the added vehicles obey traffic and have reasonable motion. The added vehicles are hard to distinguish from the real ones.
So that one is fake.
Additionally, multiple objects can be added to the scene and interact with each other, such as dynamic lane changing and turning.
The one in front of us is fake.
We can simulate consistently across reasonably long time horizons. Also, notice that GeoSim's retrieval-based approach from real data allows us to simulate flashing braking lights. Notice that in this scenario, the simulated vehicles are
All
moving
those
at high
cars are also
speed
fake.
and look reasonable,
They don't exist.
creating
in
an
the
interesting
reality.
scenario. Being 3D aware also means we can also do multi-camera simulation that is physically plausible. Here's the top view that shows one of the side cameras, while the bottom view shows the main front-facing camera. The GeoSim simulation is consistent for both sensors. Here are some additional qualitative examples.
All right, so this is all that I'm going to show you today. But basically, I talk about perception, prediction, motion planning, vehicle-to-vehicle communication, as well as simulation. There is many more things that we do in the lab. But I hope that this at least gives you a big picture into what is the kind of technology that we develop that is very different than what you see out there in terms of our competitors, and why we are developing this technology, but really looking at self-driving with a new lens in terms of deep learning as well as probabilistic inference, instead of looking at it from a robotics perspective, as most of the teams are actually doing out there. Thank you very much, and looking forward to the questions.
Thank you very much, Raquel. This is very exciting. You covered an enormous amount of ground here in terms of everything that you have. So as a first question, you start with LiDAR. Is there a way to do it without it? Or is LiDAR absolutely fundamental to self-driving car?
Yeah, great question, Gerard. I guess one that everybody but Elon Musk, I guess, might agree on. Let's see. So, do you need LiDAR to solve the task? No. The reason why I say no is because there's the proof that humans can do it without LiDAR. Now, is it much easier to do it with LiDAR? Absolutely yes. Right? Is it much safer to develop this technology with LiDAR? Yes. So from my point of view, right, is about how can we safely develop and accelerate the deployment of this technology, and for that, LiDAR is at this point a must. The same as you could also do it with as little compute as possible, with more compute, right? That's another choice, but definitely, for me, it's an accelerator of this technology. Now, there is 2 million people that die every year on the roads, right? So there is a lot of things that this technology can do in order to save lives, and also reduce the cost of transportation, give transportation to people that is very difficult right now, etc. So for me, it's a no-brainer. Like, we should use LiDAR. Now, what I didn't show in this presentation today is that our methods use really LiDAR, radar, as well as cameras. I simplify a little bit here in the drawings and whatnot in some of the papers, but obviously the system uses everything.
Okay, thank you. So a question from Thierry Bolt. For the distributional modeling work, given that there are unseen events, would it make sense to use distribution for open set detection and supporting fatter tails than a mixture of Gaussian can support? Maybe something like extreme value theory, Weibull, which has one more parameter per distribution.
Yeah, great question. So let's see. So I'm not a believer of mixture of Gaussian, so I'm happy to just toss that. So I say that through my talk. It's really finicky to train these systems in mixture of Gaussian. So, and in the case, for example, of the P3, the last end-to-end neural motion planner, is fully non-parametric. So it definitely takes into account all sorts of things there, like without the distributional issues. And now, in terms of red events and OpenSet, there is some work that we have done in the lab that we made public already in terms of OpenSet, where basically you have extra categories that are beyond the categories of interest. And we just made, I think, publicly a couple of 2 or 3 hours ago, one more work on this direction as well, how to do this really sophisticated, especially aware neural networks. So definitely this is very important. So yeah, great thoughts. Yeah, definitely something that our the system that actually runs on the vehicle definitely uses OpenSet. And now, typically, when you publish papers, you want to isolate certain components so that you show the goodness of that component alone. So that's why you will see a lot of streamlined things from, in terms of the things that we make it publicly available.
Okay.
Just to showcase that actually, that that novelty actually really works with respect to, other choices.
Well, we had a number of questions, but we are out of time. So again, thank you very much for giving us this great overview of where we are and a glimpse of where we are going with this self-driving technology. I think you have you have advanced the state of the art in a number of areas. And again, thank you very much. We hope to see you next year, maybe really live in Hawaii. So again, on behalf of the audience, thank you very much.
Thanks, Gerard, and thank you everyone for being here. My pleasure.
All right. Bye-bye. Bye, everyone.